All right, here we go. The last slideshow on our vectors unit. So bear with me. Let's get through this. So we're going to talk about the dot product and the cross product of vectors now. And within each of these main topics, we'll talk a bit about the applications you can have with them. All right, so let's start with the dot product. This is very similar to matrix multiplication when we did the row by the column stuff. So if you did, a 1 by 3 by 3 by 1, and you just went with the first, second, and third values. That's exactly what we're going to do here, and you're going to always get a scalar number for this. So it's basically like you're going to take the two x's, multiply them together, add that to the product of the two y's, add that to the product of the two z's. And that's how we do it algebraically. So this is that part. We can also find the dot product geometrically, where you're going to take the magnitude of vector A, multiply it by the magnitude of vector B, and multiply that by the angle between the two vectors. Now, usually we don't know this, so we kind of tend to rearrange this formula and use the magnitudes in the dot product to find the angle between two vectors. So let's say we have two vectors, j and k, and we want to find both the dot product and the angle between. So let's start with the dot product. It's also called the scalar product. There we go. So if we're going to do j dot k, first we're going to take the x of j, multiply it by the x of k, add that to the the y of j, multiplied by the y of k, and add that to the z of j, multiplied by the z of k. You do all the multiplication, you should have hopefully negative 8 minus, I realize on my notes I did this wrong, minus 3 minus 5, and then you will get negative 16. Okay, so if we want to get the angle between j and k, we're going to take that original formula that we had that said the dot product between two vectors is equal to the magnitude of the vectors multiplied by the angle between them. And we're just going to rearrange. So in this case, I'm going to be looking at the dot product, and I'm going to change this to say j and k, excuse me. Okay. Dot product of j and k divided by the magnitude of j times the magnitude of k. Sweet. Now that's pretty hideous, but it'll work out. Now we already have the dot product, so let's get the magnitudes. And remember, to do that, we're just going to take the root of all the values squared. And that should give you root 14, hopefully. And same thing for k. And not quite as nice, root 42, and leaving it just like this for now. So we basically have this thing that says cos of theta equals the dot product, which we found already to be negative 16, divided by negative 14, root 14 divided by root 42 as well. Okay, so we spin that around, arc cos, and if I do that math, I should get somewhere around this, and then I should get the angle between the two is 131.3 degrees between these two vectors. Now, does that make sense? Yeah. Think back to trig, cosine is negative. When you have a negative cosine, you have to be in the second quadrant, and we are. So that's all good. So let's take a look at how we can apply this. If we want to discover if two vectors are perpendicular or orthogonal, which is a word you'll see a lot, but it just means perpendicular. I mean, you can use perpendicular at 2 or 3 dimensions. They use orthogonal when you get all fancy schmancy, but it means the same thing. Okay, so when you are perpendicular, you are square, the angle between them is 90. So the cosine of 90 is 0, which means if we were going to do this setup where we said the dot product of a and b is equal to the magnitudes times cosine of theta, and theta was 90, we get this. So how do you test? If the dot product of two vectors equals 0, that means they're perpendicular. Okay, so this one, we are just going to test that. So we're going to do the same thing. We're going to find the dot product. I take the x values. I didn't name these vectors because I'm getting tired. We take the y values, and we take the z values. We're going to have 12 plus 6 minus 18. And if you do the math, that equals 0. So yeah, these are perpendicular or orthogonal vectors. We can spin it around and we can solve for some pieces knowing that if they are perpendicular, their dot product will be 0. So if we wanted to look at a dot product for these two vectors, x times 4, I'm just putting it as I see it, and then we're going to do plus 3 times negative 1 and plus x times negative 2. And if it's true, the dot product is 0. So I get, making this look a little better, 4x minus 3 minus 2x equals 0. 2x minus 3 equals 0. 2x equals 3. X equals 3 over 2, or 1.5. So the vector described by 1.5, comma 3, 1.5 will be perpendicular to 4, comma negative 1, comma negative 2. So talking about scalar projections, and this is a bit physicky. When you do a scalar projection, it's like the shadow. So it's the length of this, the magnitude of this piece when you have a shadow of A onto B. And the important thing about the scalars is to notice the wording. Shadow of A on B. So on B, so whatever it's onto is the value that goes below there. So the scalar projection of A, vector A onto vector B, dot product divided by the magnitude that of the vector that has been projected onto. So don't put an A down here because that would be the projection of B onto A. You have to do projection of A onto B. We'll take a look at a couple. So we have C and D, and we want to do the projection of C on D, and then the projection of D on C. So from our thing, we know C on D is going to be the dot product. And I'm going to set up exactly the same way because we're going to notice something else here. And it's going to be divided by the magnitude of vector B. And here, D on C, divided by the magnitude of vector C, D onto C. Watch the wording. So we're going to take, same thing, get the dot product, so we're going to take negative 7 multiplied by 2, add that to 3 times 8, and then we're going to add that to negative 4 times negative 1. Straight up dot product. Okay, magnitude of vector D. So we look at D, and it's the root of all the values added, 2 squared plus 8 squared plus negative 1 squared. So when we do this and do all that math, you should end up with 14, hopefully, over root 69. And that is a scalar projection of C onto D. Now we're going to do the other one. And I'm going to do it the same way. I'm going to do D first because I said the dot product of D on C. But we're going to notice something about dot products. Minus 1, that's a 1, times -4, and then it's going to be over the magnitude of vector C, -7 squared, and when you do that math, you still get 14. So for the dot product, it doesn't matter if you do C dot D or D dot C, you're going to get the same value. So there's two scalar projections. That's the scalar projection, which is like the size. Like if you were pulling, remember that physics problem where you pull the block at an angle and you want to know the force that you get in the x direction? That's your scalar. The vector projection is the vector in the b direction. So it's a component of A, the parallel component of A in your direction B. So when you do this math, you get a vector. You don't get a scalar. And here we go. It's going to be the dot product again. And it's going to be divided by the squared magnitude of B, which is the same as B dot B. So I think on your formula sheet it's written B dot B, but that is exactly the same as this. And then we multiply it by the vector B to get those kind of IJK coordinates. So back to vector projection C and D. So let's write down what the formula will be first. I'm going to And I'm going to cheat this because we've already done some of this math. And we're going to multiply that by vector D. And down here, and multiply that by vector C. So we knew that the dot product was 14. So both of these are going to have 14 as a numerator. And we knew that the magnitude of D was root 69. So if I square root 69, there we go. We know the magnitude of C was root 74 from the other side. So if I square root 74, okay. And then I'm going to put some brackets around it, and it's up to you whether you, this is like a disgusting thing here, so you can just leave it separate and just write down to 8, -1. If you're more comfortable, you can absolutely incorporate it. That was D on C, and -7, 3, 4, but this is fine. Okay, so that's that kind of piece of vector described going in the C direction in this case, or going in the D direction in the first example. Cross products. So when you make a cross product, and there's lots of physicsy magnetic field applications to this, but for you guys, I think when you make a cross product, you have this plane created by your two vectors, and the cross product will be another vector, another vector that is perpendicular to them. So that's my shitty drawing. There you go. And what happens, where to use that for you guys, it's rendering light. And I read somewhere that if you're doing a first-person shooter, it kind of gets you're up or you're down, depending on which way you're doing, A cross B or B cross A. So when we look at this, if we take A and it has these values, and we take B and it has these values, A cross B is ugly. So it returns a vector, an IJK, or the square bracket vector. And you'll notice that when you see this, it's kind of like, for the I value, it's the Y's and the Z's subtracting each other, and for the then that's for X, and then for the J value, it's the X's and the Z's, and for the K value, it's the X's and the Y's. So it's the stuff that it isn't, but there's a good visual way to do this that I like a little better. So first thing is you're going to take your two vectors. I've got L and M here. I'm going to write down ijk twice, and then I'm going to write down the xyz twice. So this is L here, M. So write your first one first and your second one second, because these are slightly different. And when you want to do this, so if you are looking at the first term, the I term, you're going to start at the I on the top, and you're going to make an arrow. So you're going to do 3 times 5. And then it's always a subtraction in between. And then you're going to do whatever gets you back up to an I. So you're going to end at the I, so you have to start at this -1. Weep. There we go. So, and that's going to be the math for your I. So I'll put a little massive brackets around it. And I'm going to try and switch colors here and go for the J. So the J is the same thing. You're going to start at the J. You're going to go diagonally down. So you get -1 times 4. And you always subtract your up direction. You have to end at the J. So you get 5 times -2. And I'll put those in big brackets. And that's your J direction. And then we'll put another plus and switch colors one more time. And let's do a green. For K, I'm going to start at the K. There's my first multiplication. -2 times -1. Coming back up again to hit the K. -4 times 3. K. Just running right out of room. There we go. Okay, so when we do all that math, you should hopefully get 15 minus 1, 14i. And then you're going to have -4 plus 10, 6j. And then it looks like 2 minus 12, -10. Or 14, 6, -10. So a vector that is parallel to the plane created by L and M is going to have this direction. We're going to try a couple more, and once again we're going to compare what the cross products of C cross D looks like compared to D cross C. So same thing, I, J, K, I, J, oops, I pressed the button, hold on. There we go, K, and this time we have -7, 3, -4. And -7, 3, -4, and then 2, 8, -1, 2, 8, -1. And maybe I'm going to try and work in one color, hopefully. That is a little less obnoxious. Okay, so we start with the eyes. So down we go. So -3 minus, and I have to hit the eyes, -32 equals 29 I. Okay, let's look at the J's. Trying to hit those right numbers. -8 minus, I'm trying to be super careful, 7, because negative times negative. Okay, and that should be -15 J. And then if we go over to the K's, -56, and back up to the K's, minus another 6 is negative 62k. So C cross D equals this. All right, I've magically drawn the second one because no one wants to sit here and watch me draw it, but we will get to watch me do the process. So we're going to go down with I, negative 32, minus, we're going to go back up to minus 4, and that's going to give you negative 29I. And with the J, you're going to get positive 7, minus 8, which is going to give you positive 15J. And any guesses about the K? Yeah, it's going to be plus 62K. So there you go. If you do C cross D, and you want to know what D cross C is, you're just going to reverse the sign for everything. Because it really, at the end of the day, if you do a right-hand rule and you're thinking of physics, if one is up this way and one is down that way, they are going to just be opposite signs. So applications of this. Here I'm going to use C and D again because we've already found it, even though the numbers are disgusting. So finding a unit vector perpendicular to two vectors. So really, what we want to do is that plane that those two vectors are in, I want a unit vector, but I only want it to be one high. So if you remember before, it would be the value of the vector. So if it was, x, y, z divided by the magnitude of the vector. No diff, we've created this cross product. This is a vector, so that was what goes on top. I think for you guys, that'll just give you something that you can scale to any size if you have the unit vector. And we're going to put that over truly foul root, which will be the root of 29 squared plus negative 15 squared plus, I forgot the negative, doesn't matter. Okay, so you're going to end up with 29, negative 15, negative 62, and by my calculations, when I do that math over something really nice, the root of 4,910. You can leave it like this, you can incorporate it, you can get crazy with the radicals. I think for the test purposes, they tend to look like this. So you have found a unit vector perpendicular to two vectors when you do that. And one last time looking at this picture, finding the area of a parallelogram. So if we have a situation where we've got A cross B, when you find there's the vector, but conveniently the magnitude of the vector will actually end up being the area. So one last time, I'm going to be lazy. Let's pick 1, 2, 3 as one vector, and our second one, we're going to cross it with 4, 5, 6. IJK, IJK, and then 1, 2, 3, 1, 2, 3. I almost wrote down 1, 2, 3, 4, 5, 6, and then 4, 5, 6, 4, 5, 6. Switch the color. Let's go with aqua. 12 minus 15. 12 minus 6. 5 minus 8. So there's a cross product. So now I want to know the magnitude, remembering these signs always rep the magnitude. And we're just going to do the same old, negative 3 squared plus 6 squared plus negative 3 squared. Do all that math, and the area of that parallelogram is the root of 54, so 7 point something or other. So those are all the things I want you to kind of look at for this vectors test. Hopefully it makes sense.